Welcome everyone to this webinar. Today we're going to talk about ANC headphone testing. First of all, I'm going to introduce myself. My name is Santiago, and I'm a global support and application engineer. I'm part of the global support team for both gross sound vibration and audio precision as part of the Axiometric Solutions group. And first of all, I would like to mention some basic things on housekeeping items that we should know. You probably already noticed that you are all muted, so you won't be able to speak during this webinar, but there's gonna be, there's actually, if you look in the dashboard of the GoToWebinar platform, you will find a Q&A, a section called questions, where you can write all your questions and there will be time by the end of the webinar to answer some of these questions. There's another section called handouts where you will be able to download some of the interesting material related to this topic. That includes the slides of this presentation, also application note related to headphone testing in general, and then a technical note that is mentioning how to perform ANC measurements using audio precision software and GRASS test fixtures. This webinar is being recorded, so you will be receiving a copy of it in a couple of days from now. So let's look at the agenda for today. It's actually many topics that we have to cover. So we are expecting to be here for around an hour, maybe a tiny bit more. First of all, I'm gonna introduce the company. We're gonna have basic definitions related to ANC, some of the most important considerations whenever we want to perform one of these measurements. We're going to talk about relevant standards, test setups with different complexities. We're going to talk about the ANC test itself and its challenges, also how to measure the noise introduced by ANC circuits. Then I'm going to show you some of the GRASS test fixtures and AP hardware, data acquisition systems and solutions and software for measuring ANC. And by the end, I'm going to show you a video presentation especially made for this webinar, where I'm showing you how to use the AP software to perform an ANC test together with a GRASS test fixture. So I already mentioned Axiometric Solutions Group. Maybe some of you never heard of it, but basically Axiometric Solutions Group is owned by Battery Ventures, which is a global investment firm that has around 38 years of experience with more than 400 investments. So these three brands that we see here, AP or Audio Precision from United States, GRASS Sound Vibration originally from Denmark, and IMC Test and Measurement originally from Germany, are three of the brands that are part of the Axiometric Solutions portfolio. So we are basically helping engineers, technicians, and researchers with tools such as electronic, audio, and electroacoustic test instrumentation, high precision measurement microphones, and also productive test and measurement systems. The idea is that with solutions provided by these three brands, engineers and technicians can capture signals that are out there in the world with sensors such as measurement microphones from GRASS, for example, and then you can use measurement software and data acquisition systems like the software and data acquisition system provided by AP and IMC to analyze these signals and gather some insights based on your findings. On the right side of the screen, you can view a representation of some industries that are served by brands in Axiometric Solutions. So these are ranging from audiology, automotive, and also semiconductors, among others. So let's start with the main topic of this webinar, the ANC headphone testing. And in order to start, we're gonna try to define what's the meaning of ANC. And it basically stands for active noise control or active noise cancellation. And it's a method that we use to reduce unwanted sound by adding another sound source that is specifically designed to cancel the original sound source. And here we have an example of this. We have a noise source that it could be traffic noise, it could be the noise from the metro, it could be the noise from people talking around you in a library. You get the idea. And then we get a receiver. So the noise from this noise source is getting into the receiver. It's arriving to the receiver. But then we can have a system with a microphone that captures the signal from the original noise source, amplifies, and then does some kind of processing. And this could be some kind of DSP unit, or it could be an analog circuit that is basically inverting the phase of the captured sound signal, and then using a sound source to produce a signal that will interact destructively with the original background noise, reducing the noise that is perceived by the receiver. Another definition that is important to talk about is what is passive noise control, passive noise cancellation, sometimes called as PNC. And it's basically the sound reduction by using noise isolating materials such as insulation or sound absorbing tiles or mufflers and so on. So in the case of a headphone or a headset, it would be the material that is used to build the headset. So we can use a combination of different materials, more massive materials with higher density, to try to absorb the sound as much as possible before it enters into the ear canals of the person using the headset. So the passive noise cancellation is usually most dominant at higher frequencies. And what are higher frequencies? It's usually in the range of around 900 to 1.5 kilohertz. And this is for a typical system, INC system inside a headphone. And then the active noise cancellation is most dominant at lower frequencies. And this is typical frequencies below 1.5K or below 900 hertz, depending on the system. And here we have an example of that. This is a typical result of an ANC test where the green curve is showing us the open ear situation. The light blue curve is showing us the passive attenuation of a pair of headphones, and the violet curve is showing us the passive plus the active attenuation. We can see that more or less around 1.5, 1.7 kilohertz and above, the passive attenuation is the most dominant type of attenuation, while below that the mentioned frequency, it's the active noise canceling that is most dominant here. Now we need to have some considerations so we are all in the same page when it comes to what's the meaning of ANC testing. First of all, we have to make a distinction. We have the electroacoustical tests and we have the audio electronic tests. Let's start with electroacoustic test. This is basically when we have microphones and or loudspeakers within our signal chain. So the microphones in this case could be the ANC microphones that are in a headset, like we see over here, these two microphones. Or it could be on the loudspeaker, sorry, it could be the loudspeaker that we are using as a sound source to create a noise field around the device under test. If we talk on the other side about audio electronical tests, these are tests that are typically performed at test chip level. That means that there are no microphones or loudspeakers involved in the signal chain. That is when I'm connecting, for example, a signal generator directly into the inputs of my ANC chip. And then I'm taking the signal directly on the outputs of the chip with a cable, and then I connect this to the audio analyzer. Today, we are going to concentrate on electroacoustical tests. And that doesn't mean that the analyzer of the software that we are going to show today can't be used for audio electronical tests, because you can use it actually for both situations. But today, we are concentrating on electroacoustical tests. And now it's time to make some distinctions or some clarifications related to electroacoustical tests, because sometimes when I mention ANC to an engineer, it might mean a slightly different thing to another engineer, for example. So what do I mean by headphone ANC? it's basically the active noise cancellation is designed to remove the background noise so you or the person that is wearing the headset can stay focused on the work or have a better music listening experience. That's the definition of ANC for this webinar. This is the type of ANC in electroacoustical measurements that we are going to look into today. And I'm trying to make this distinction because then we have another thing that is called, or I usually call, headset microphone noise cancellation. And this is basically when we are using the microphones to remove the distracting background noise, so the person that is calling you and is on the other side of the line will not hear that background noise. So this is the basic distinction between headphone ANC test and headset microphone noise cancellation. Today, we're gonna talk about headphone ANC in electroacoustical test setups. Now that we're talking about headphone ANC, and especially for the people that are getting introduced into the topic, there are different ways where we can make our ANC circuits. And that would be by using different type of microphone techniques. And one is called the feed forward, and the other ones are called feedback microphones. If you see here on the right, the feed forward microphones are placed on the outside of the DUT, while the feedback microphones are placed in the inside of the DUT. And nowadays, we also have hybrid solutions that are taking advantage of both techniques, using feed-forward microphones, but also controlled feedback microphones on the inside. There are pros and cons to all the different techniques mentioned today, but we are not going to get into this differentiation today. It's just so you know that there are different ways that microphones are used to perform the headphone ANC, the noise control. And then there's one last thing that is the ANC his noise. And this is by default when we are introducing a circuit to an active circuit to reduce the noise inside the ear of the person wearing the headset. We are going to introduce some electronical noise that might be amplified by the loudspeaker inside the headset. And this his noise might be annoying for the user. So we want to measure the signal and we want to characterize the signal in order to improve the performance of the circuit and try to reduce the noise as much as possible. We will see during this webinar that both GRASS and Audio Precision are providing complete solutions for measuring ANC headphones and headsets. So now it's time to talk about relevant standards. And unfortunately, at the moment, a national or international standard concerning noise reduction performance of ANC headphones doesn't exist at all. It doesn't exist. However, we can use some closely related standards as guidelines. So they can give us some hints of the type of setups or the procedure for measurement that we need to use for ANC testing. And two of these standards are mentioned here. One of them is the ISO 4869-3, measurement of insertion loss of hearing protectors. And the other one is the ANSI 12.42, methods for the measurement of hearing of insertion loss of hearing protection devices with continuous or impulsive noise. Here I'm also mentioning some standards just for your information. These two standards are related to headphone measurements in general, and the three standards over here are related to ear simulators or head and torso simulators that are typically used for headphone testing. I'm just leaving this here for your information just in case you want to check them out. But most of the test setups that we are going to describe today are based on this first ISO standard, the 4869-3. So let's go to the next slide where we can see an example of a setup. Now, the ISO standard I just mentioned is basically recommending, or the main recommendation it does, is to perform the measurement inside a reverberant chamber, because it wants us to use a diffuse field for the measurement. It's also pointing us to a very specific type of test fixture with a very high self-insertion loss. We're going to talk about this later, which is a fixture like the GRASS 45CA that we see here. It doesn't specify the right amount of loudspeakers. This is just an example. But the idea is that with these loudspeakers, we create a diffuse sound field around the test fixture, and we're going to use the reference microphones to measure the to measure how diffuse is the field around the fixture, to see if we are complying with what the standard sets. The test signal that this ISO standard is recommending is the pink noise. So we are going to play back pink noise in these loudspeakers inside a reverberant chamber. We're going to create a diffuse field. We're going to double check how diffuse is our field with reference microphones, and then we're going to perform the measurement with and without hearing protectors. So this is the base we're going to take for our ANC measurement test. We can make this setup more complex or more simple. But the basic thing we need to consider if we want to look at the amount of channels that we'll need for our data acquisition system and the outputs of a signal generator, we'll basically need 2 channels for our ear simulators. So inside the test fixture, we're going to have left and right ear simulators with the measurement microphones. And these 2 outputs of the microphones are going to be connected via a microphone power supply to the audio analyzer. And then on the other side, on the generation side, we're going to have the outputs of our signal generator, that it could be 1 output for each loudspeaker connected to an audio amplifier, and then sending the signals through all the loudspeakers. Let's remember that the DUT, the headphones or the headset, doesn't need to be connected to the analyzer, because we are not sending any signal to the drivers in the loudspeakers itself. We are exciting the ANC microphones in the DUT by producing a reference noise signal with the loudspeakers. So here we say that we can have 1, 2, or non-reference microphones, and these measurement microphones can be used to test how diffuse is the field around the fixture, or they can be used to test the background noise in the test environment, or they can be used to test this level that is being produced by the reference signals coming from the loudspeakers. But we can use none of these microphones if we want to simplify the test and just rely on the microphones that are inside the test fixture for that measurement. So how many loudspeakers do we want to use for the sound field simulation? We have to remember that the more loudspeakers we use, the more analyzer outputs we will need, and therefore the more amplifiers we will need. And also the more channels we are using, the greater the complexity of our setup, because we are going to need more equipment. So we need to know exactly what are the needs for our test. Do we want to perform a very realistic test with many channels, or want to make a quick reference test with a setup that is as simple as possible? Of course, in the real life, we also have some budget limits and things like that. And then we need to decide which test environment we're going to use. Of course, we mentioned that the ISO standard is recommending a reverberant chamber, but maybe if we are working with many channels and we want to, instead of using pink noise, we want to simulate a real noise environment, like the noise inside an airplane or the noise inside the metro or things like that, we might want to perform the test in an anechoic chamber with multiple loudspeakers. Or maybe I just want to use a quick and dirty test for a quick measurement setup in R&D, or for a quick measurement or an easy measurement within production line or quality assurance and so on. And then for that, it might be just enough to use a small test chamber where I can fit the test fixture and less amount of loudspeakers. So no matter the complexity, a setup will typically look like that, with more or less loudspeakers, with or without reference microphones. We have a setup with an audio analyzer that is generating a signal that is going to the loudspeakers. The test signal is measured by the ANC microphones, and then is captured by the microphones that are inside the test fixture, and then sent back to the analyzer for analysis. This is what we call a closed loop measurement. So when I use the closed loop term here, I refer to a classic audio test where a reference signal is generated by the audio analyzer here, and then it's input to the device under test. So the resulting DUT output is immediately sent back to the analyzer for analysis. So this is the closed loop measurement. So the signal is sent back to an analysis. For analysis, everything is done in a continuous operation. So the analyzer is working both as signal generator, but also acquiring the signals for analysis. And I'm mentioning this because we can also have a setup in an open loop measurement. And this would be a perfect example of that. So the open loop here is to refer to a test in which the audio signal is not generated, passed through the DUT, and analyzed in one continuous operation. So here we don't have one continuous operation. We are using a completely different system for signal generation and a completely different system for signal acquisition and analysis. And this could be in cases, for example, where we already have a software to perform the background noise simulation, and maybe want to keep on using that. You can still have a setup like this and use an audio precision system as for acquiring the signal and analysis and doing the signal analysis. And if we want to go to a very simple setup, for those of you who don't want to go through the trouble of creating a diffuse field or the trouble of having 16 or 500 loudspeakers to create a very realistic background noise environment, we can have a setup like this, and we can still get a reasonable estimate of the ANC headphone performance just by using a pair of stereo speakers, or as in this case, a single mono loudspeaker that is going to be placed in front of the test fixture. No reference microphone. We are going to use the microphones inside the test fixture to measure the noise floor of the test environment. So this setup can be put together inside of a small test chamber, for example. So we don't have to use a big anechoic chamber or a big reverberant chamber for this. And this is done in a closed loop situation. I'm going to be referring to this test setup later on when we're going to do the demonstration. So let's talk about the ANC headphone testing performance itself. So what are the steps for getting the result of the ANC test? First of all, we need to select the type of signal we want to use. And this signal is going to be used to create a noise field. So this could be a pink noise signal, for example, if we follow the recommendation of the ISO standard, or it could be a very realistic signal with multiple channels, like simulating the metro noise or something like that. You get the idea. For the measurements, we are typically performing a frequency response measurement using an FFT or octave analysis. It could be 1/3 octave, 1/6 octave analysis, and so on, but basically a frequency response measurement. The first measurement we are going to perform is with open ear. By open ear, I mean that we have the test fixture without any headphone or headset. And then with the test signal off. With this measurement, we're going to be measuring the ambient noise inside the test chamber. For the second measurement, still with open ear, that means without DUT, we're going to turn on the signal generator with a big noise or whatever signal we're using, and then we're going to measure the baseline of the noise with open ear. With these two measurements, we can already calculate the signal to noise ratio. And as a rule of thumb, the signal to noise ratio should be at least 10 dB, comparing the open ear situation with the situation where the DUT is already mounted with the ANC turned on. This way, the measurements can be, we are sure that the measurements result we're getting are as reliable as possible, and that the background noise of the test chamber is not affecting the measurement. For the third part, we're going to mount the headphone for the first time. We mount the headphones on the test fixture. We keep the test signal on the generator on, but we're gonna make a frequency response measurement with the ANC function turned off. And then for the last part, we're gonna do the same measurement, but now we are gonna turn on the ANC function of the headphone or headset. So we are basically going to steps to get these results. First of all, the signal to noise ratio, which is step 1 minus step 2, the passive attenuation, which is step 3 with minus step 2, and then the active plus passive attenuation, which is step 4 minus step 2. And these are the curves which are seen before during this presentation. We are going to do something like this during the video demonstration. So let's talk about some challenges. This is basically to get an idea of the challenges you might encounter while doing ANC testing. We can't, of course, address everything, and we can't talk too much about all these challenges during this short webinar, but this is just so you get an idea. First of all, I'm mentioning the sealing or the leakage. For the ones of you that are already have experience with ANC, you know that if the user is not placing their headphones or headset very well around the pinna, if there's no good sealing, you might hurt the performance of the ANC for that headphone or headset. And this is the same case when we are having a setup like this. We must be very careful that there's a good sealing between the DUT and the test fixture, so we can ensure that we are measuring the right or the best performance of the headphone when the headphone is properly mounted on the test fixture. The second challenge is getting a high self-insertion loss test fixture. And this recommendation is coming from the ISO standard and the ANSI standard that I mentioned in the beginning. This is basically because the maximum amount of ANC that we are going to measure is going to be related to what's the self-insertion loss or the self-insertion loss of the test fixture. So for example, if we have a test fixture with a very low self-insertion loss, that will limit the maximum amount of ANC performance that we'll be able to measure for the test fixture. So we want to make sure to get a very high self-insertion loss test fixture so we can measure the ANC performance properly. The microphones we are using inside the ear simulators on the test fixture, they should have a proper dynamic range so they can handle the signals that we are going to use for the test. And this could be very high sound pressure level signals, or it could be very low sound pressure level signals. No matter in which range we are working, we should be able that the sensitivity of the microphones that are in the test fixture is high or low enough to handle these signals. Then in some cases, the ANC is also used, not only used for headphones and headsets, but sometimes for hearing protection devices. So some of the things that we are going to see during this webinar are applicable to the people working with ANC for hearing protection devices. Then I talk about realistic soundscape versus simple measurement setups. When I say realistic soundscapes, I'm not only referring to complex realistic background noise like metro noise or library noise or things like that, but also by artificially adding reverberation to the background noise signals, or adding wind or interfering talkers and things like that. Sometimes we want to make the measurement as realistic as possible, and sometimes we want to make the measurement very, very simple and have a very simple setup. Something to consider, depending if you're using a very realistic background noise measurement signal or a pink noise that would be considered something more like a simple signal, is that some headphones can perform different with realistic environments than pink noise. So pink noise is not very realistic itself, but can be good enough for quick comparison test or quick performance test of the ANC. Some headphones also could be optimized to perform well on pink noise, but then they will perform poorly on realistic environments, or vice versa. So this is something to consider. The test environment, especially background noise, is something we need to consider. We might look for a test chamber that has a background noise low enough that won't affect the measurement, so we can have the right signal to noise ratio for this measurement. And then we have objective versus subjective ANC performance. With this, I mean that usually we just perform frequency response measurements for the ANC performance test. But it's more and more common to start using some sound quality parameters to perform ANC tests. And one of the most popular parameters is loudness, or Zwicker loudness. There's an ISO standard about it. And loudness is basically the subjective perception of sound pressure level. So it's how we humans are perceiving sound pressure level. So it's a sound pressure level measurement that considers the equal loudness curves of the human hearing model. So sometimes it could be that we find a device that might be performing very well according to the frequency response test, but then when we add sound quality parameters, the headphone might not be performing as well. So this is another thing to consider. Bluetooth devices, we say that the DOT doesn't have to be connected to the analyzer, but ANC measurements are typically performed in the context of a lot of other headphone measurements. So if we are dealing with a Bluetooth headphone or headset, we might want to have an analyzer that is already compatible with Bluetooth headphones and headsets, so we can perform all the measurements in the same within the same measurement system. Circuit noise, this is something we're going to talk about it later. Then music quality when ANC is on. Sometimes when we are listening to music and we turn on the ANC function, we might perceive that the quality of the music is lowered. This is something to consider as well. We don't have solutions for everything. We don't have recommendations on how to measure everything, but these are things that we need to consider. And then we have something new, that is the adaptive or adjustable ANC. So depending on the background noise you have around you, the ANC circuits might change the amount of processing that they are doing depending on the signal around you. So if you want to test that, you might consider a signal that is changing in level, that is adding interfering talkers, that is changing the type of noise over time. And of course, there are other challenges besides the acoustical challenges, such as battery life or the headset size. This is more important for example, true wireless headphones. The size of the headphone we want to make it as small as possible, and the ANC circuits are going to take some space, and there's something we need to consider. So let's talk about test fixtures. Here I'm showing you 4 types of test fixtures from Grass. The first one, the 45CA, this is the most popular and the most used test fixture for this type of measurement. This is the one that is recommended by the hearing protection standard, the ISO standard that we see here. It's perfect for the solution because it's small, but it also has a very high self-insertion loss. It's very massive and heavy. It has more than 60 dB of self-insertion loss. You can see all the self-insertion loss specifications in our website. You can equip this test fixture with many different types of ear simulators. If you can use a realistic pinna, such as the anthropometric pinna. So this is like the most used configuration for ANC test, and this is the one we are going to be using today. Then we have the 45CV that is based on the 45CA, but it has this human-like shape in the head. We also have different type of pinna. This is a test fixture that is made according to this ANSI standard. It also has, just like the 45CA, very high self-insertion loss. It can be It has a very long ear canal because this is made for testing earmuffs or earplugs originally, but mostly for situations when we have impulsive noise, such as in construction environment or for the military, for example. So this is another popular test fixture. Then we have the KEMAR. The KEMAR is a head and torso simulator. So we have a very realistic human-like test fixture with a very well-known head-related transfer function. So it will affect the sound field in a similar way that a human person will affect the sound field. So this might be important for some of the users. We can also have this test fixture configured with a mouth simulator if we want to test microphone parts of a headset. But the thing to consider is that the self-insertion loss is a bit lower than the fixtures we have seen before. And last but not least, we have the 45cc, and this is the most popular headphones when it comes to regular headphone testing. And it's very versatile. We can equip this in so many ways. We can even include a mouth simulator. We can have many different types of ear simulators and rubber pinna and so on. It's very, very flexible. We can change the dimensions of the whole fixture to accommodate different sizes of headphones and headsets. The problem with this is that the self-insertion loss is way lower than the other fixtures that we have seen before. So this is something to consider whenever you are performing an ANC test with a fixture like the 45cc. Let's now take a look at analyzers. You know, Audio Precision is providing a very big range of audio analyzers. And today, I just want to give you 3 suggestions that it could be used. They could be used for this ANC test. This doesn't mean that these are the only way of measuring ANC with AP analyzers. This is just 3 suggestions that I'm making. Let's look at the example setup number 1, where we are using an APX 517. Some great things about this analyzer is that it has a built-in audio amplifier. So that means that we can connect the audio amplifier directly to a passive loudspeaker to use as a sound source for the test. Then it also has a built-in stereo amplifier. So in the case that we are also using this analyzer for testing wire headphones, we can still use this analyzer for that and not only for the ANC test. We have a built-in microphone supply, and this is great because we can take the outputs of the test fixture and connect them directly into the analyzer without the need of using any other external equipment. We can provide CCP power supply or also plus 48 phantom power. And then we also have one slot over here for digital input and output modules. In this case, it's configured with a Bluetooth module, but you can use other modules such as digital serial or HDMI and many others. And this is great if we are using the analyzer, for example, for also testing Bluetooth headphone and headset. We could use a Bluetooth module in here for measuring everything within the same ecosystem. But what are the things to consider here? Well, the first limitation is that the amplifier here is only a mono output of 35 watts, so we can't really use a huge high power loudspeaker, and we can't use multiple outputs for powering loudspeakers. So it's only for very simple setups like the one we're going to review today. Then we have a single slot for digital IOs. That might be more than enough for this test. Actually, you don't really need it for the ANC test, but you might need more than one digital IO module depending on the other tests that you are doing with the analyzer. And you only have 2 microphone inputs. That means that we can only connect left and right of the test fixture. We don't have more channels if we want to use reference microphones. The setup number 2 is using an APX 515 analyzer and an APX 1701 transducer interface. So with this setup, you get 2 analog inputs to connect the left and right channel of the test setup, of the test fixture, sorry, and 2 analog outputs. With this analyzer, you don't have a built-in power amplifier or a built-in microphone supply, and that's why we are adding the 1701. The 1701 is giving us a stereo power amplifier output of 100 watts, and then the 2 microphone inputs, and then this can be connected together with the APX 515 analyzer. And then if we need more channels, we can consider a setup like the third setup. with the APX 585 analyzer and the GRASS 12BB power module. With a setup like this, we are getting 8 analog inputs and 8 analog outputs, and we also get 3 slots for adding digital input-output modules. So here we need to consider the following: that we will require active loudspeakers or external audio amplifiers, because this module doesn't have a built-in power amplifier like the 1701 or like the 517. And that we will require a power module like this, like the 12BB, to drive the microphone. So with this 12BB, we have 4 microphone inputs that are connected to the inputs of this analyzer. So we can have left and right of the test fixture, and we can have 1 or 2 reference microphones if you want. And then with this one, we have 8 analog outputs that we can use to drive 8 amplifiers for 8 loudspeakers, for example. But if we have the possibility of having digital I/O slots, we can use a module, for example, like the HDMI. We can send 8 channels via HDMI to an HDMI amplifier. We can create our we can have 8 different speakers, for example, that are driven by an HDMI amplifier. So these analyzers I just showed you are connected via USB cable to a Windows computer running the APX 500 software from Audio Precision. And this is one of the most advanced audio measurement interfaces available right now in the world. So we can basically create very complex measurement procedures and automated sequences that include user prompts, measurement limits. We can call to external application, and everything can be created directly within the software interface in a very easy way, without the need of having any programming skills at all. And that will help you saving a lot of time and, of course, money. You can also create custom interfaces and application-to-application automation using the Audio Precision APX API for this. So if you know programming, we are providing extensive documentation with examples for Visual Basic.NET, C#, MATLAB, LabVIEW, Python, and so on. So then you can share all your projects and all your automations with other APX units anywhere in the world. And we are basically offering a lot of solutions for electroacoustical testing, both for R&D and production. You can do perceptual audio testing like POLC and PESC, speech intelligibility, and most common electronic audio measurements out there. So we are using a common software platform that is making the test and the results easier to share between production line and R&D. And we are offering with each analyzer you buy, each hardware analyzer, you get a perpetual license for use the software. But we are also adding, if you want to, you can have a subscription license model, so you can be always getting all the latest updates. And concerning updates, and this is something very important to mention, is that APX software gets major updates every year, and we've been doing that for the last 15 years. So every year, at least you get 1 major update and sometimes 1 or more minor updates between these major updates. So the software is constantly updating. We are constantly listening to your feedback and adding new features to the software. And the newest software is supported even in old analyzers. We actually have analyzers we sold 16 years ago that are still supported and can use the very latest 2022 version of the APX software. So that's something important to consider. And for the last part of this webinar, before we get into the video demonstration, I'm going to talk about the noise introduced by electrical circuits. So you know that more of the headphones and headsets today are including circuits such as ANC or Bluetooth. And these electronic circuits are creating a very low level of hiss noise. This hiss noise can typically be heard by the person wearing the headset, but with traditional test equipment, the traditional test equipment we use for testing headphone, we can't really measure this noise because it's usually below the noise floor of this traditional equipment. So at GRASS, we have developed an ear simulator that is using the technology of low noise microphones with very high sensitivity that reduces the noise floor of the whole system. So we are able to measure these type of signals. So these measurements typically performed in an anechoic chamber with a very low background noise. We use a test fixture with low noise ear simulators inside. Then we place our headset with ANC capabilities on the fixture, and then we just turn on the ANC and we just try to capture this hiss noise with the fixture. So here in these curves, first the dash curve over here is the human ear threshold. This is the sensitivity of an average human ear. The red curve is showing us the standard, the noise floor of a standard ear simulator like a 711 coupler. This is the most common type of ear simulator used for measuring headphones. And then here below, the light blue curve, this is the low noise, the noise floor of the low noise ear simulator from GRASS, the 43 dB low noise ear simulator that we see over here. So you can see that we have an area of this curve here that we have a lot of signals that we should be able to hear with our ears, but the standard testing equipment won't be able to measure because it's below their noise floor. But with a new low noise ear simulator from GRASS, we should be able to measure these signals without any problem. And here we have an example of that. We are placing a KEMAR head and torso simulator inside an anechoic chamber with a very low noise floor. We're gonna measure the background noise, the blue curve over here of the test chamber. Then we mount the DUT on the test fixture and we perform another measurement. And after that, we're going to turn on the ANC functionality of this headset. This headset in particular has 2 levels of ANC, and you can see the noise that is introduced in the measurement when we are just turning on the ANC. There's no other signal in the test chamber. It's just turning on the ANC capabilities, and we just hear the hiss noise. We can measure the hiss noise thanks to the low noise ear simulators. So this hiss noise, as we can see, is below the noise floor of a standard measurement system. But thanks to the low noise ear simulator from GRASS, we have a 30 dB better signal to noise ratio, and we are able to measure this self noise of the ANC circuit. So now we can measure the signals that we can hear. These low noise ear simulators are available standalone as a 43 dB like we see over here, but also in a test fixture like the 45CA or head and torso simulator like the GRASS KEMAR, as we see over here. So, summary from everything we have talked about so far. We have defined what's the meaning of ANC, of active and passive noise cancellation. We talked about the difference between electronic test and electroacoustical test. We talked about the standards, and we really don't have any specific standards, but we can use especially the ISO standard as a guideline to try to propose a test setup. We've seen test setups with different complexities. We talked about how to perform the ANC test. We talk about hiss noise test, and then I show you some of the GRASS test fixtures and the AP analyzers and software. Now we are going to continue with the video demonstration. This is a video I made specifically for this webinar. It's a bit more than 15 minutes. And I'm gonna describe the whole setup during the video. We're gonna see pictures of the measurements. Most of the measurements here are based on this technical note 141 from Audio Precision. You can download this technical note from the handout sections, but you also can go to the AP website following this link and also download the project file, the AP project file related to this tech note. You should double check your Windows audio settings because the video I'm gonna play back now, it's taking into account the Windows audio settings and not the GoToWebinar audio settings. So you can always go to your Windows and check that you're using the right device over here. So if you don't hear sound at the instant I started playing back the video, then just double check your Windows audio settings. Otherwise, you will also receive a recording of this webinar with the video as well. So here we have the APX 500 project. As you can see, we are working on version 7.1 and in the sequence mode of the software. If we go to the left in the navigator panel, we can see that this project is called ANC Headphone Test and that it has two different signal paths. Signal path number one, called calibration of ear simulators, where we are going to measure the sensitivity of the two ear simulators in the test fixture, and signal path number two that is called ANC measurements, where we are going to perform the ANC measurements themselves. This project also has two different sequences, one for the ANC measurement and the other for the calibration of the ear simulators. Just so you know, a sequence within APX 500 software is a collection of checked items that might include signal paths, measurements, results, and sequence steps. And for this demo, I'm going to run each different sequence separately, and I'm going to step through all the different sequence items so we can understand how this test is implemented with this specific project file. So the first thing I'm going to do is run the calibration ear simulators sequence that includes the signal path number one, as you can see in this checkbox over here. But before doing that, I'm going to show you some pictures of the setup that I'm using today. As you can see, I have the 45CA test fixture from Grass. This is the version of the 45CA that is using anthropometric PINA with high frequency ear simulators, the Grass RA402. This is the test fixture together with the DUT, which is a headset with ANC capabilities. And here we have a picture of the setup inside the anechoic chamber, where I can see that I'm using loudspeaker as a sound source. And this is a full range loudspeaker that has a woofer and a coaxial high frequency driver. As you can see, it's placed at a very close distance from the test fixture. This is another picture of the setup and one last picture of the test fixture. Let's go back to the project file and let's run this first sequence, the calibration of ear simulators. I'm going to press play. And as you can see, I get a pop-up window that prompts me to perform the right connections. And this is a very simple setup where I'm using the Grass 45CA together with the APX 517 audio analyzer. As you can see, the left and right channels coming from the test fixture corresponding to the left and right ear simulators are connected directly into the unbalanced microphone inputs of the 517. This version of the 45CA has prepolarized microphones with CCP preamplifiers, and these CCP preamplifiers can be connected directly into the APX 517, and this is because the 517 has built-in microphone power supplies to drive this type of technology. The 517 also has a built-in power amplifier, which means that I can connect my loudspeaker, which is a passive full-range loudspeaker, directly into the 517 without the need of using an external audio amplifier. So once I'm sure that all the connections are made correctly, I can continue with the sequence by clicking OK, and then I will get a new prompt, in this case for calibration of the left ear simulator. Now this specific version of the 45CA with anthropometric pinna requires a partial disassembly of the fixtures so I can access the ear simulator and mount it inside a sound calibrator for the sensitivity calibration. For this test, I'm going to be using a 94 dB at 250 Hz reference signal. As you can see, I haven't inserted the ear simulator inside the sound calibrator, and that's why right now I'm only measuring noise that you can also see here in the FFT meter. The frequency box is also marked in red because I configure my system to measure a frequency of around 250 Hz. Now I'm gonna mount the sound calibrator in the ear simulator channel. As you can see over here, I'm gonna configure the sound calibrator with a signal of 250 Hz and 94 dB. And if you look at the software, we are detecting a frequency of around 251 Hz, which is within the tolerances that I configure for the system. If you look at the levels behind the prompt, you can see that the left channel, which is the blue channel over here that I'm calibrating right now, the level is still measuring something that doesn't make sense. And that's because the sensitivity of the channel hasn't been populated yet. And that will happen once that I press OK. And now you can see that the system is measuring around 93.9 decibels, and that's because I'm using a correction factor for this ear simulator that is 0.09. Now it's time to calibrate the right ear simulator. So I mounted the ear simulator inside the sound calibrator. And as you can see, we're already detecting the frequency coming from the sound calibrator. And once I'm going to press OK, the sensitivity will be corrected. So I will be able to measure the correct level in the system. And you can see over here that now the right channel is measuring around 93.9 decibels because I'm using the correction factor, as I mentioned before, of 0.09 dB corresponding to this specific calibration setup for this ear simulator. If you see at the FFT, you can see the 250 Hz signal coming from the sound calibrator. If we open the calibration box from the APX 500 software, you can see that here we have the configuration that I set for the calibration prompts. Even though the sound calibrator is producing a 94 dB SPL calibration signal, I am telling the system that I should be measuring 93.91 dB SPL, and that's because of the 0.09 correction factor that corresponds to this specific calibration setup. And this information, you can find it in the manual from the 45CA in the calibration section. So here we have the different sensitivities that we just measured by using the 42AG sound calibrator. Now there are different ways of performing the sensitivity calibration of the channels. If we can't or we don't want to use a sound calibrator, whether we don't want to partially disassemble the test fixture or because we don't have time for it, or we are okay with accepting higher levels of uncertainties with the measurement results, then I could use the TETS chips for calibrating the signal channels. In order to do that, I have to click on the TETS syscheck box, and then if my test fixture is compatible with TETS, I will be able to read the TETS information from the preamplifiers inside the test fixture, and then I could use the sensitivity information that is recorded inside the test chip to apply these values in the different signal channels. The fixture I'm using today is not compatible with TETS, so I can't demonstrate this functionality. The good thing is that most of the new GRASS test fixtures, including the 45CA, have TETS functionality. So you will be able to perform a calibration with TETS if that's what you want. So the first thing we're gonna do is I'm gonna show you in detail how the first signal path for the calibration of the ear simulators is made. I'm gonna open the signal path, and then I can see that in this folder called the sequence steps, I have all the different prompts that we have seen when I run the calibration of ear simulator sequence. If I double click on the prompt, then we can see all the details related to it. So you can edit and write whatever you want in here, and you can change the appearance and also do a preview of the prompt. Uh, Next step, we also have these prompts for calibration of left and the right ear simulators. We can edit the prompt over here. And the key thing related to the calibration prompt is that we are going to tell the system that for the left ear simulator, whatever we are measuring with the sound calibrator, we're going to set the reference for the channel 1. We can also check the appearance of the prompt, and we can preview the pop-up window in here. So as I said, now for the right ear simulator, I'm going to tell the system that we are going to set the reference level, in this case for channel 2. That's going to be the right ear simulator. So now it's time for the next part of the measurement that corresponds to the sequence related to the ANC measurement itself. In order to do that, I can change the sequence from the navigator by clicking on the drop-down menu and selecting the ANC measurement sequence. As you can see, now I have different elements that are selected within the navigator. I'm going to be using signal path number 2 for the ANC measurement. I will expand the signal path to see what's included on this sequence. And as you can see, besides the signal path setup, I have two different measurements that are the basics for this sequence. First of all, I'm going to be performing a signal to noise ratio measurement and then the ANC measurement itself. So now I'm going to run the sequence. The first thing is that I get a prompt to insert the ID of the device under test. That could be the serial number of the headset. I'm going to press OK. Then I get, once again, a wiring diagram to double check the connections. I'm using a 45CA that has 2 ear simulators that are connected directly into the microphone inputs 1 and 2 of the APX 517 analyzer. And I'm using a single full range passive loudspeaker that is connected into one of the outputs of the power amplifier that is built in the APX 517 analyzer. For this test, I'm going to be using a pink noise reference signal. That doesn't mean that I can't use another reference signal, but for the sake of this test, I would like to keep it as simple as possible, and that's why I'm using a single mono output with a pink noise reference signal. So as I told you before, this sequence includes a measurement that is called a signal to noise ratio measurement. For this measurement, The system will first of all measure 10 seconds of the background noise within the test chamber, and then another 10 second with the reference signal turned on. As you can see, the device under test is still not mounted on the test fixture. So that was enough to measure the signal to noise ratio. Now it's time to measure the ANC performance. And as you remember from the presentation, the first situation would be the open ear measurement, where the DUT is still not mounted on the test fixture. And I'm gonna play the reference signal in an open ear situation. So for the next step, it's gonna be situation number 2, where I have to carefully mount the headset on the test fixture with the ANC function turned off. And for the third situation and final step, I'm going to keep the headset mounted on the test fixture, but I'm going to turn on the ANC function. So once the measurement is finished, we get this nice report. So the sequence was configured to create a measurement report where we can see all the results. Of course, this report can be configured in any way you prefer, adding more or less results to the report itself. Let's go back to the APX software and let's analyze all the different steps corresponding to the ANC measurement sequence. So as you can remember, the first measurement we performed is the signal to noise ratio measurement. In order to do that, there was no DUT mounted on the test fixture. Under these conditions, we measured the noise floor in the test chamber. This is measured from the ear simulators of the test fixture. And then we turned on the signal generator with the reference signal, which was a peak noise signal. With these two measurements, we can calculate the signal to noise ratio and we can analyze if the results are good enough for the measurements we are about to perform. So the next measurements are the ANC performance of the DUT. So this result we see over here shows the 1/6 octave spectrum for the three conditions for the left and right ears. Let's remember the three conditions. The first one is the open ear situation with no DUT mounted on the fixture. Then we have the second situation that corresponds to the DUT mounted with the ANC turned off, which corresponds to the passive attenuation of the DUT. And for the third situation, we have the DUT mounted on the test fixture with ANC on. This corresponds to passive plus active attenuation. To make sense of these results, we can use a compare derived result within APX to normalize all the results to the open ear result. So here I'm showing you the results for the left earphone. The blue curve is the open ear result compared to itself, which will constitute an open ear reference. Then the blue curve is corresponding to the DUT mounted on the test fixture with the ANC turned off. This is a passive attenuation. As we can see in this lower part of frequency range, there's a resonance going on, and this is because of the cavity of the headset itself. And then on the green curve over here, we have the performance of the DUT with the ANC turned on. So this is showing us the passive plus active attenuation. So this DUT has some attenuation going on compared to the passive result up to around 1.5, 1.7 kilohertz. this same result is shown for the left and the right earphone, and they are also expressed as insertion loss results if we want to. So this concludes the demonstration for the ANC test performance, and we can go back to the webinar. Okay, let's go back to the presentation. So as you can see, this was a very basic demonstration. Of course, you can complicate things much more if you want to add way more channels, if you want to use realistic signals, and so on. But I hopefully this was enough for you to get an idea of the basics. Of course, you could also calculate total like single value total attenuation results with the AP software with that derived result as well. So many things are possible within the software. So this was the last slide of this webinar. I can see there are lots of questions here, so I'm going to try to answer to all of them. Let's see, which correction curve is applied to achieve this flat open ear curve, or are these recorded by free field reference microphone? I think that this was already explained during the video section. I'm the green curve. Let me go back to here. The green curve, it was basically comparing the open ear situation to itself. So I was measuring the open ear situation, yes, and then I was adding a compare derived result within the APX software, comparing that curve to itself. So I get this reference flat curve in the system. Regarding testing for ANC, how representative is pink noise for real-world situations? Well, I definitely wouldn't send device to the market by using only pink noise signal nowadays. There are so many other things to consider, where the thing is that if we only use pink noise, then we really don't know how the headset is going to behave, or the ANC algorithm is going to behave with more realistic environments. We don't really find, or it's not very common to find pink noise in realistic situations. So I would say that pink noise is it's a good signal to get an idea of the performance of the ANC, but it's not the only reference signal that we should use. Maybe pink noise is good enough for a quality assurance system setup, or for some quick measurement in R&D, but it shouldn't be the only type of signal that we use for this test. Can you use the GRASS45CA microphones without the headphones on it as a reference microphone for the ANC headphone testing setup? Yes. You don't really need to use the reference microphones. If you want to simplify your setup, you can do it by just using the measurement microphones inside a fixture for measuring the background noise, if you want to. And this is what we have done during the video presentation, for example. When would you prefer using an open loop setup over a closed loop setup? Actually, as I already mentioned in the presentation, it could be that you already have a software for a recreation of background noise or realistic background noise situations. So if you want to keep on using that, then I would probably use an open loop situation. Otherwise, let's say I have a very complex system using more than 16 channels, for example, something that the APX analyzer couldn't handle, these very special niche situations, then I would consider an open loop situation. Otherwise, I would just keep it simple and try to make everything in a closed loop measurement. How do you translate test results for ANC to all the different king of inner ear features people have? I really don't understand this question. So if you can clarify once again, otherwise you can write me an email. We are leaving the emails here. Give me a second. support@grossacoustics.com, tech support@ap.com. We have noticed before that during testing, we are able to hear the thud of footsteps while ANC is on and walking around. Is there any way to mitigate this? Well, we are not actually designing ANC circuits ourselves, so I can't really give you a recommendation related to that. If I'm misunderstanding your question, please write me an email and then we can discuss this further. Will there be a version of KeyMark compliant with P57 type 4.3? Okay, for the ones that are not familiar with the ITU P57, it was very, very recently updated with a new section describing ear simulators. This is a type 4.3 section. At the moment, GRASS doesn't have anything to offer that is compliant with this section, but who knows in the future. Right now, we do, if you want to measure up to 20 kilohertz, for example, we do offer our high frequency ear simulators that are still complying with the IEC 6318-4 standards, the 711 coupler standard. So if you want to reliably measure up to 20 kilohertz, we can recommend to use these ear simulators. How to set up an APX 525 analyzer with the APX 1701. This is for the ones of you that you're not familiar with 1701. The 1701 is this transducer interface. Basically, you can interface this APX 1701 with any APX analyzer. So basically, you are connecting the 1701 via USB to the computer, to the same computer where you have connected the analyzer, and then the APX 500 software will automatically detect that the 1701 is connected, and you will be able to see the inputs and outputs in the software. So you can use it with any analyzer of the APX hardware line. Is there a way to directly measure loudness or residual noise instead of attenuation during testing? At the moment with the APX 500 software, we don't have the sound quality parameter called loudness. But you can also, using the sequencer, you can export the results, do some operation outside APX and import the results within the same sequence. And as I also mentioned during the APX software presentation, we are constantly updating the features of the software. So who knows, maybe this is a feature that is added in the future. Will the project file from the video also be available as reference? Yes, you can go to this TechNote. You can go to the handout section, download the PDF slides, and then you will find this link to the website where you can download the TechNote 141 that includes the PDF of the TechNote, but also the project file from APX software. You can also search for TechNote 141 directly on the website as well, on the AP website. Can we apply A weighting, C weighting, etc. during measurements? Yes, you can do that. You can do that in APX software, no problem. How do you take into account the time varying noise. Well, we wanted to make a very simple setup here with just a ping noise used at one single level. So if you want to take that into account, you should use a more realistic signal, maybe that is changing the level over time, for example. And you can also do that in APX. You can use whatever signal you want to, and then you can, for example, make a transfer function measurement within the software. Is it possible to run measurements without a silent or anechoic room? Yes, of course it's possible. I mean, there are no standards right now on how to perform a measurement of ANC. So these are just suggestions. I think one of the most important things to consider is the noise floor of your test environment. You don't want your colleagues working around you to disturb your measurement. And of course, you don't want to disturb your colleagues around you with the high sound pressure levels coming from loudspeakers. So that's why we use a test chamber. So yeah, you can just use a small test chamber, for example, if you want to. For the ANC video demo, how was the octave spectrum generator level? Selector. Well, in order to measure, to do the octave analysis measurement within the APX software, you have to download the octave analysis plugin. You can download that from the website. If you have any questions about that, you can send me an email and I can show you how to download it. Just a free download, you install it, and then you can do octave analysis within the software. Someone is sending a clarification to the question that they found out that inner ear channels of a lot of test people to be very different. ANC seems to work very different based on seal and depth of ear channel. Yeah, this is a very important challenge. I think the first thing to consider is that in order to be able to compare one device under test to other, we need to provide the same conditions for the test fixture. So we need to know that the measurement system of the DOT, was measured within the same conditions. That means using the same noise signal in the same test environment and using the same type of test fixture with the same type of ear simulators, for example. If we are using let's say that everything is the same, but we use a test fixture that has different ear simulators, then we can't really compare those results because the two different ear simulators might have a different way of loading, acoustically loading the device under test, or they might have a different frequency response. So we, first of all, need to make sure that we have exactly the same conditions in the whole signal chain to be able to compare one DUT over the other. And of course, if you're not sure about the ceiling around the test fixture, you can make multiple measurements, trying different positionings of the DUT on the test fixture until you can find the best performance. That might require a couple of tries. How can we calculate signal to noise ratio using the APX 500 software? Well, first I did a noise measurement without any signal, and then I made another measurement with signal. If you download the project file of the APX, it doesn't matter if you don't have an APX analyzer. You can open the file in demo mode, and then you will be able to see all the sequence, and you can see exactly how first I measure the noise, then I measure the noise with the signal in both open ear situations, and with those two results, I can calculate the signal to noise ratio. What EMC test standards has gross hardware been tested to? I really don't remember the numbers, but everything is following with the specifications of the European Union. You can send me an email and we can discuss about that. Will I be able to get the recording of the presentation? Yes, in a couple of days from now, you will get the recording of the presentation. That's no problem. One of my colleagues from ATMES in Germany, representatives there, is telling me that they have a solution for measuring loudness within APX software. Thank you for that. What is the impact of self-insertion loss on measurements? Well, the passive noise attenuation of the DUT is more or less a self-insertion loss measurement of the DUT of the headphone in this case. If the test fixture we are using has a lower self-insertion loss than the headphone itself, then what we are going to be measuring as a result of our test is the self-insertion loss limit of the test fixture itself. And that's why we want to make sure that the test fixture has a high self-insertion loss. And something important to consider that is actually clarified in the ISO standard is that the self-insertion loss of a test fixture like the 45CA that we have used today is not following any, it's not related to the self-insertion loss of an average human skull or anything like that. It's basically providing a very, very high self-insertion loss. So we are sure that what we are measuring is the self-insertion loss of the hearing protector in this, in the case of the standard, and in the headphone in the case of the webinar today. Should I prefer high self-insertion loss or low self-insertion loss? If we are talking about the fixture, it's always better to have a fixture with high self-insertion loss, of course. So we can properly measure the attenuation of the headphone without being impacted by the self-insertion loss limitation of the fixture. That seems to be the last question. Let me see. Yes. If I missed any question, you're welcome to contact me. You have the emails here. Remember, we are going to provide you with the recording in a couple of days. And that's it for today. Thank you very much for participating. It's been a pleasure. And I will see you in the next webinar. Thank you very much.